my name is Russell Haering. I'm a software development manager. I actually work here in the third floor of this building at Rackspace. I work on a product called OnMetal, which you guys just learned a little bit about. So OnMetal is a two-way user. It appears as a set of flavors in the Rackspace cloud. So this is a list of the flavors we have available, and you can see there's all the kind of virtual machines and stuff. But right here you've got 3 flavors of what we call OnMetal. And the thing that's different about it is that it's bare metal. So where normally when you're interacting with an OpenStack cloud, you're interacting with a virtual machine, you're kind of creating them, destroying them, doing all that stuff on demand. We are doing all of those things, but with bare metal. And so at its core, OnMetal is really kind of a union of open compute hardware. And so this is open source hardware. It was kind of originally developed by Facebook, but now there's a whole bunch of companies that everybody's heard of involved. Microsoft, all these kind of big companies are coming together and basically open sourcing hardware designs that are fantastic for running clouds on. And so we kind of thought, instead of just using this to build a standard virtual cloud, why don't we build a bare metal cloud on top of that? And to do that, we're using not only the kind of standard Nova and some modified Neutron, but also an OpenStack service dedicated to provisioning of bare metal or iron called Ironic. And so I tend to get 2 questions when I start talking about this. And the first question is kind of like, why bare metal? And that has its root in the idea that we have virtual machines. And so aren't we just introducing a whole new set of problems when we start trying to do things with bare metal? Does that even make sense? And some people will attack it from another angle. They have a closet full of servers, and they understand why bare metal because they have a bunch of it. But the question is, why automate bare metal networks? Because it's in a closet. We set up the networks, now we're done. We're going to go ahead and deploy Nova or what have you on top of that. And the answer to that, from my perspective, is I work at a hosting company, and so I don't just deploy a closet full of servers. We deploy a server for one guy and then a server for the next person that comes along. We deploy servers every day, and sometimes people want to get rid of their servers. And so it's a much more dynamic environment. And what we see happening is that there's this data center of the future kind of emerging. And at its core, it's not getting any less automated. And so, where we're not some people just have this closet and they're just doing kind of a one-time thing to it, where it's constantly changing for us. And so we want to have the best automation that we can to do that. And that may mean that we're just provisioning bare metal for somebody else to install a standard OpenStack cloud on top of, or some other cloud. But every time you see a virtual machine, underneath it there's hardware. And we want to automate that as well as possible. Now before I get into this, what I want everybody to kind of be thinking about throughout the rest of this presentation is that the last 2 presentations were fundamentally about software innovation in networking. So everything that you saw presented, and you saw 2 kind of different approaches to how you could build a virtualized network topology. And both of those approaches are very much rooted in the ability to innovate in software. And so be thinking about that as I go through this. Back on track. At the hardware layer in OnMetal, it's pretty standard stuff. So you have 2 10 gigabit Ethernet interfaces. They're connected to a pair of top-of-rack switches. So every server is connected to 2 switches. So if we want to take one switch down for a software update, or the switch just goes down because that's what they seem to do a lot, that's OK. We also have a single 1 gigabit connection that we use for kind of out-of-band control of the server. But users of the server don't see that, and so I'm not going to really focus on it here. When you boot an OnMetal server, if you look at the disk, there's always kind of a root disk. So we have one flavor that has more disks for data, but in every single flavor, you have a root disk. It's a 32 gigabyte flash device, and there are 2 file systems on there. And so the first of them is the one listed first here, and that's your operating system. So if you installed Ubuntu or CoreOS or something on there, that's what you're going to see. SDA1, it's your file system. At the very end of the disk, and it's 30 gigabytes or less, we have one that has a label of config-2, and that one is special. It's a OpenStack config drive, and where normally in a virtual cloud it would show up as kind of a CD-ROM drive attached to your virtual machine, we can't attach a CD-ROM drive, or not a dynamic CD-ROM drive, to every physical machine when you provision it. And so we've just stuck it at the end of the disk there. And the reason that this is interesting is because inside of that config drive partition, we have a bunch of JSON files. And inside one of those JSON files, we reference, down at the bottom here, network config. And the traditional approach to this in OpenStack is that they generate a Debian-style interfaces file, and they stick it in the config drive, and they basically say to put this at /etc/interfaces, which is great until you're not running Debian. So if, for example, you boot a CoreOS box, it's not going to take a Debian-style interfaces file. And so what people end up doing is they parse the Debian interfaces file, and then they instead generate like whatever the kind of local default config file is. CoreOS actually does it a little bit differently, but like on Red Hat, this thing called CloudInit parses the Debian file and generates a Red Hat-style file. We've replaced the Debian thing with JSON. That's still kind of the basic functionality there. Now, in terms of what the actual network looks like, so you have your pair of physical interfaces. We bond those together, and that kind of does the HA component. So if one of the switches goes down, like if ETH1 is connected to the switch that goes down, then the bond continues to work. And on top of the bond, we basically expose individual VLANs. And from the server's perspective, each of those VLANs represents what Neutron calls a network. From inside the server, you see 6 interfaces. You have your normal loopback. You have the 2 physical interfaces. You have the bond. And then you have the actual VLANs. In this case, there's just 2 of them. That's fine. On the control plane side, things get a little bit more interesting. And so again, this is in the today scenario. So when you go to boot a new server, and this is normal OpenStack, so Nova calls into Neutron and basically provisions what it calls ports for your server. And port is a virtual concept that exists in a virtual cloud world, and it does not represent a physical port on a switch. It's kind of this like virtual idea of a port that is connected to your virtual machine. So then Nova goes down and calls out to Ironic. The way that we make the kind of Nova to Ironic interaction work is that Ironic pretends to be a hypervisor in order to kind of trick Nova into booting machines on it. And then inside of Ironic, we actually call into Neutron and say, OK, we have like virtual port X. Now map that to physical switch port Y. The way that Neutron does this today, and this is where things get really ghetto, Neutron SSHs to the switch and configures it on the fly. And then we have a particular variety of Cisco switch that requires really a lot of prayer and then a little bit of hope to go with it. What we do is that we pin ports to specific VLANs, IP addresses, and MACs so that you can't spoof a different IP. You can't like pretend to be an IP address that you're not. And you also can't sniff traffic that's destined to an IP address that's not yours. But this has a lot of really obvious problems. The first is that you have really limited tenant isolation. So although you can't sniff or spoof things, you basically, if you want to use this, like if you have your database, if your MySQL instance is running on an OnMetal server, you need to use IP tables and maybe something at the application level. You need to use something beyond just like, I know it's on an isolated network, it's OK, to secure that database. Another limitation is that due to the way that whole kind of config drive flow works, is you cannot modify the network configuration at runtime. If you were to, for example, attach another network to the server, that can't be automatically reflected on the server because we don't have a way to propagate that down into the server. And then there's kind of a limited ability to introduce virtualized kind of functions in the network. So a lot of the cool things we were hearing about earlier, just you can't do that because we don't have any kind of virtualization on the network. And this gets to the root cause, and this is kind of upsetting for me. So switches we think of as a black box. Like nobody says, oh, I'm going to like SSH into my switch and I'm going to upgrade like some software package. They don't do any of the normal things that you would do on a server. People aren't mostly running configuration management against their switches. Switches are, I thought it would be interesting to include this list of Cisco certifications, and it was like, there's really a lot of them. These are like the things that you're supposed to have to administer a server. So like my team has this guy, and he's I don't know which of these he has, but he's a brilliant guy who knows all about Cisco switches, and we asked him to SSH into a Linux box, and he didn't know what to do. And this was like fascinating for me because he's a brilliant guy. He solves every one of our network problems, but he has no idea how to work a server. And to me, a switch is just a server with some like fancy network cards in there that runs some software. And so that kind of is getting to what I was mentioning at the beginning of this talk, with we're seeing all of this innovation, this really cool software things, and mostly they're not available on switches. So like even the most recent presentation we just heard, he was mentioning that they have the VTEP support, but the way that the VTEP support, as I understand it, works is that it has kind of an OVSDB layer on top. And so instead of them putting their really cool like technology onto the switch itself, you have this kind of layer between like the mediocre stuff that exists in switching vendor world and the really cool innovative software that all these people are building. And so that's kind of what we're looking at for the future. It's like, it's better. We get the isolation, we get kind of that virtualization stuff, but it's not as awesome as I would love it to be. So realistically, for OnMetal, what the future probably looks like is that we have Neutron, and it's going to talk to NSX. And that's exactly how our virtual cloud works today and a lot of other people's. NSX is a network controller, kind of similar to what we were hearing about earlier. It's very centralized. And there will be an agent on switches that talks to NSX. And that's probably the OVSDB protocol, unless we can get really aggressive and put our own code on the switches. And there will be something either on or off the switches that talks to Neutron. So maybe we're able to put software on the switches that talks to Neutron and pulls down certain bits of configuration that we can't get over through the NSX controller. Maybe we'll still be SSHing to them, or something kind of in the middle. A lot of switches these days are exposing APIs that are better than SSH, but still aren't like I can just drop a container on the switch. On the data plane side, it'll probably look like VXLAN between switches. Tim, was that it? Yeah, so Tim was mentioning that they, for some things, they are doing different tunneling than GRE. In our world, it's likely to be VXLAN because that's what's supported in hardware on anything with a Trident 2 chipset, which is most switches these days. And you can do the same thing on in a lot of NICs. And so that the VXLAN tunnels will go between the actual switches and between hosts in our virtualized cloud. So in other words, the physical switches will basically be providing exactly the same functionality that a compute node in a typical virtual cloud is providing today. And so there's a lot of challenges here, and I've kind of mentioned a lot of these, but like number 1, 2, and all the way down to 10 is that we are treating switches as kind of special appliances and not just a fancy server with NICs in it. And so the software that I want to buy doesn't exist today, and it's getting really close. Fundamentally, there's one problem for us, and it's because we have those 2 switches, the HA pair of switches. I cannot go out today and buy a switch that has support for software-defined networks that is HA and works. And if I want to write it myself, and I do, because I'm a software guy, that's like what I want to do. Seeing a problem like this, I want to write it myself. I can't operate it in a normal fashion. Mostly I can't put it on a switch at all, but that's actually changing it a little bit. So Cisco, Cumulus, Nicira, a lot of vendors are now exposing the ability to put software on switches, but mostly it's not normal. So the closest to normal is Cumulus. Who here has heard of Cumulus? Cool. So Cumulus Linux for switches, it makes a switch look like a Debian server. And that's, it's almost exactly what I'm begging for here. But it's a Debian server. And the problem is, what if I don't use Debian? And there's a side problem of that it doesn't look exactly like a completely normal Debian, but it's getting really close. The other problem here is that protocols are kind of treated like black magic. So like Tim was talking a lot about Zookeeper and some things that CoreOS might be doing. And all of these are problems that any software engineer can pretty trivially understand. Right? I actually have programmed against Zookeeper a dozen times. It's not that hard. We're synchronizing down state. We have like lookups in a hash table. These are all problems that software engineers can solve. But today the protocols are kind of very black magic-ish. And they're very complex. And so if I were to, for example, buy one vendor's controller, it's unlikely that I will implement the protocol myself. in order to kind of do a half and half of what does one vendor have over here, and even just my own stuff, much less mixing two vendors. And then finally, the kind of efforts at making all of this open just aren't there yet. They're actually getting really close, so I don't know if anybody's been following it, but Facebook has announced they actually worked with Broadcom to open source a kind of an SDK for the Trident 2 chipset. So you can now actually write code which makes this chipset do the interesting things that you need it to do. And so like we were hearing earlier, there's kind of this interface between user space and kernel space. On switches, the kind of kernel space is actually mostly in hardware because you can't make a Linux kernel in software do things at the rate you would want it to in a switch. And so they kind of specialize the hardware a little bit. So like Facebook is working with Broadcom, we can actually begin to kind of start doing these. Tim?
So that's a question I was going to ask is Cumulus still has the problem that they have to pay for the Broadcom SDK
Yeah.
for the ASICs?
Yes.
Do you think that problem will be solved by going around them or some other way like Facebook is trying to do?
Sure. So Tim's question was about whether we think that we can go, or that somebody can go around paying for the Broadcom SDK, because Cumulus today has to pay for it. Yeah, I mean, that seems possible. So like the most straightforward route around it is to just run Facebook's kind of open switch operating system, which when I looked at it, didn't look done. I would love to do that. Really one of the things that I'm kind of getting at here is that where like if I want to put software onto a server, I can do that with a team of one. Putting software onto a switch is not something I can do with a team of one because a switch is viewed as fundamentally different. Maybe I can kind of work on the Facebook switch operating system, but I'm like writing components of an operating system, which is just much more challenging than just putting software onto an operating system. I mean, I don't want to predict the future, but the price of Linux isn't going up. And I think that the price of Linux on switches is going to go down too. So, whether that means that we just use the open source Broadcom thing or something else, I don't know. And I guess I've been going on this for a while, but this is my ideal, is just like switches are just servers with fancy NICs. We can put software on them and do all of the things we do to servers today. We can treat them just like a compute node in an OpenStack cloud. We get an ecosystem of like software abstractions around switching ASICs, so things like the Broadcom SDK, but maybe with higher level abstractions on top that make it easy to develop against. And then an ecosystem of libraries for control protocols so that I can code against Zookeeper and it's not that hard, but I would love for there to be even higher level abstractions so that I can basically just go and kind of cobble together like, here's a thing for talking to my ASIC, here's a thing for talking to the switch controller, and switches just become another service on the network. And that's all I'm after here. Yeah.
So comes back to your first principles of what problem you're trying to solve. But why didn't you just do? I mean, why couldn't you do all this at layer 3?
Yeah.
Collapse the problem to something, a tiny fraction of what you've had to solve here.
So, are you suggesting like basically like push everything out like up?
Routed access design with security groups on the server.
So, if the security groups have to be pushed down to the server, we don't want to do that. Our goal is that we don't want to have to push any work down to the server, right? So like we can actually do security groups today, we're working on it, but it's going to be implemented as like ACLs in the switch. It's all right. We don't want to have to push any work down to the server. Our goal is that, because we can't trust the server. For us, like the server is untrusted land, and so the very first thing that we can trust in the stack is the switch. And so anything that can't happen in or above the top of rack switch, we treat as something we're not going to do. Does that make sense? What else? Yeah.
How do you deal with the stateful nature of security groups and switching ASICs not having memory between connection state?
Sure.
Connection state?
You do that in, well, okay, so I'm going to do this in two parts. So the question is about what do we do about the stateful nature of security groups and challenges with ASICs not having memory. So in today's world, if we build security groups in our current kind of non-virtualized model, it's going to be just a matter of we have a Neutron plugin, and that's actually what this thing here is, which that's the thing that SSHs out to switches. And it will kind of, when we do this, continually check on the switches and say like, hey, is that still up to date? Because in particular, these Cisco switches we have will reboot at random and forget everything they ever knew. It's a little frustrating. We're working on it, making progress, I'm sure. In the future, when we can put software on the switch, then we can basically say, we can put that, like push it down into the ASIC, and once it's there, it's not going to go away until the switch reboots, at which point we can put that back in there before anything happens. Does that make sense?
Yeah.
Yeah.
To belabor the point, but if you say you can't trust the server, what makes you think you can trust them at layer 2?
Well, we're not trusting the server at layer 2. We enforce everything in the switch. So like a packet comes out, we basically make sure that that packet is coming from a MAC address that we know belongs on that physical port. We make sure that it's going from an IP, that it claims to be coming from an IP address that we know belongs on that physical port. And so that's one of the kind of limitations of this that makes it a little bit less dynamic than we would love, because like we have to know ahead of time, this is the MAC address and this is the IP address on that port. And so like when I said, today there are 6 interfaces show up on the server, there's only 6 interfaces on the server. We can only do, today if you're using OnMetal, you only have what we call public net, which is a network that goes to the internet, and ServiceNet, which is a network shared among all Rackspace customers. Tim?
Do you continue to see switch hardware and server hardware being separate, or are you sort of buying into the Google model where everything is a server and we do it all and we improve the kernel software?
Sure. I think they're converging. So like the Facebook, in addition to their switching operating system, Facebook has open sourced and made part of the Open Compute project some like physical switch designs. They are a separate design from the Open Compute server designs, but I think that over time we're going to see, so for example, if I were to buy a generic kind of white box switch today, it would have an Intel processor, and that would not have been the case a year ago. So I think that we are trending towards the hardware and switches being much more commodity, but whether a switch will ever just be a server with some really fat network cards in it, as opposed to something with a physically different chassis, I couldn't say. My guess is no, just because form factor stuff, but I'm not a hardware person. Yeah.
Do you support multicast and how?
Yeah. So the question is, do we support multicast? The answer is don't do it. It probably will work today, but we don't guarantee that it will keep working in the future. It will in the isolated network scenario, unless we change our plan, it will likely work, just because in that case we will actually have like an L2 overlay, and so we'll actually like do kind of multicast over unicast, if that makes sense.
So if you're trying to do any gossip stuff or something, just stay with the multicast.
Yeah, probably fine. Anything else?
So how does this compare, if someone just wanted to run Ironic, they're an OpenStack enterprise
Yeah.
user, and they wanted to run Ironic to provision bare metal server capabilities,
Yes.
do they have to tackle these problems, or are you solving a different problem? in
Sure.
Rackspace?
Great question. So the question is, what happens if you run Ironic today? And this URL, which I had to make smaller to even fit on here, I would encourage you to visit that. The answer is that you mostly, Ironic doesn't touch switches or networks at all. It just kind of assumes that your networks are configured the way that they should be. And so mostly that's because Ironic, until 8 or so months ago, was mostly pushing towards this idea of like provision a closet full of switches, then hands off. A closet full of servers, then hands off. It was not really focused on the ongoing like maintenance and deprovisioning and reprovisioning of a fleet. And so it wasn't even doing things like wiping disks between deploys of a server, which for us is obviously critical. And so we are getting a lot of this stuff into Ironic, but none of our network code has landed yet. So what we have is, in addition to our Neutron plugin, We have some patches against Ironic that make it do, and also against Nova, but that's minimal, that make it do the kind of interesting components of the networking today. Okay, anything else? Perfect. Thanks everyone for coming.